Hello, good evening, what's up, and welcome back to another 1001 MSc online tutorial. My name is Brock Grant, and today we're going to be covering video 2 of Module 5, Chemical Bonds and Molecular Geometry. So, a few prerequisites for this video. So, the biggest thing I really want to emphasize is that you understand how these electrons move, how they work, and how they're involved in determining a charge of an element, and how different elements can bind together to change the overall charge of a compound, because that will be very important throughout answering these questions. So the first one will go to question 6 on page 244. So again, I recommend that you pause this video, attempt the questions yourself, and then we'll go through it and we'll try and answer it as a team. So the first question says, classify the bond between these pairs of elements as ionic or covalent. Okay, so essentially all the question is asking is just, is it a covalent bond or is it an ionic bond? So the best way to determine this is we need to draw our Lewis structures out. So if we have a look at sodium and oxygen. So if we've got oxygen, so if you look on your periodic table, you will see that oxygen has 6 valence electrons. And we have sodium, so sodium just has 1. What do these need to do to bind together to become stable? So what will happen is that sodium doesn't want to share electrons, okay? So what is easier for sodium? To just get rid of that 1 electron, meaning that it will then fall down to a lower energy level and its outermost shell will be filled, or to try and sort of share and try and steal 7 electrons? The answer, of course, is for sodium to just get rid of it, to cut its losses, and to just donate that electron to oxygen. So because sodium donates this electron over to oxygen, it will then have another electron here. Now, of course, this will require 2 sodiums, because oxygen needs 2 electrons to become stable. Because remembering the octet rule is that it must have 8 electrons in its outermost shell. And that's very important. That's absolutely critical that you have a very good understanding of the octet rule. So we actually need another sodium to donate its electron over here. So it would be, the overall sort of compound would be Na2O. And these 2 sodiums would formally donate 1 electron each to oxygen, meaning that the bond that holds them together is ionic. Now, if we look at oxygen and hydrogen, so again, we've got our oxygen. Again, as we realize, oxygen does need 2 electrons to become stable, but hydrogen, on the other hand, is where things get a little bit different. So hydrogen has 1 electron in its outermost shell, but hydrogen is one of 3 elements that are an exception to the octet rule. Now, for purposes of this introductory chemistry course, it is only required that you know hydrogen is the main exception, where hydrogen only needs 2 electrons in its outermost shell. Now, if you are getting a little bit confused about that, I do recommend you check out the atomic theory videos, as that's where I explain valence and why it is that hydrogen only needs 2. So if we've got hydrogen down here, so I'll replace this with a cross. Now again, as I've said before, it doesn't matter what symbol you use to represent the valence electrons, just as long as the markers can understand it. So if we have hydrogen like this, so we've got the valence electron for hydrogen, and we've got the valence electron for oxygen, they will sort of share. So they'll pass that electron backwards and forwards, and share it so that they both are able to use those electrons each, and this represents a covalent bond. So remember, ionic is a formal donation or stealing, whereas covalent is sharing between the 2. So because with oxygen and hydrogen, they share these electrons, it means it's covalent. Okay, let's move forward now to question 16. So the question states, determine whether each of the following atoms will form a nonpolar covalent compound or a polar covalent compound, and give the formula of this compound. So we've got 2 oxygen atoms. So oxygen as we know, which you can again look at the periodic table, has 6 valence electrons. Now, the big thing when you're looking at polarity, when you're looking at Lewis structures, when you're looking at VESPR, is again, we need to really pay attention to those that octet rule, and we need to make sure that all of these elements have 8 valence electrons in their outermost shell. I keep repeating this because it is just so crucial. Because if they do not have 8 in their outermost shell, they are unstable. They're not happy at all. So as we look here, we can go 1, 2, 3, 4, 5, 6. So these have our 6 valence electrons. However, these 2 oxygen atoms will form a covalent bond twice. Okay, and the reason for that is that they need 8 electrons each. So they're going to share 2 electrons between them. So if we have a look over here and we count them all, so 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen is happy. Then 1, 2, 3, 4, 5, 6, 7, 8. So this one is happy. So how this would look is like this. And that just shows that the electrons are nice and spread out. And again, this is how O2 would look in real life. So now that we've drawn our Lewis structure for O2, or 2 oxygen atoms, we need to now determine whether it is polar or non-polar. So all polarity is an uneven distribution of electrons. So as I explained in the previous video, imagine that it's just 2 people throwing a tennis ball. Except when it's polar, if one person throws a tennis ball, the other one will catch it and sort of hang on to it for a bit, be a bit greedy, and then throw it back. Another sort of metaphor that we can use to determine whether a compound is polar or non-polar is to picture it like a tug of war. And this is where our dipole moments come into play. So if we have a look at our O2, so our 2 oxygen atoms here, is this polar or non-polar? The answer is non-polar. And that is because in the scheme of using like tug of war to try and pull those electrons away, we have oxygen and, well, oxygen. So it's like me playing tug of war with me. You know, I'm not stronger than myself because, you know, we're the same thing. So you've got oxygen and oxygen. One is not more powerful at trying to steal electrons than the other. So because of that, it's not like this oxygen has more ability to like hold on to those electrons than this oxygen. They're perfectly equal. And it's because of this that it is non-polar. So looking now at our oxygen and 2 hydrogens. So again, we draw the Lewis structure. So when we're looking at polarity, whether we're looking at VESPR, it's very important to always draw the Lewis structure. So we now have oxygen here. We now need to put in our hydrogens. So remembering hydrogens only have 1 valence electron in their outermost shell. Now we need to make sure that all of them are stable and are abiding by the octet rule. So we have a look here at oxygen, 1, 2, 3, 4, 5, 6, 7, and 8. Oxygen is stable. Hydrogen, 1, 2, 1, 2. So remembering hydrogens are one of the exceptions of the octet rule. So that makes hydrogen here and this hydrogen happy. Everyone's happy. Happy days. Now we need to ask ourselves, is this polar or non-polar? So what I'm going to do is I'm just going to slightly rotate this water molecule just to make it a little bit easier to see. This is where we need to ask ourselves about the electronegativity. Okay, so electronegativity is just the how desperate an element is to try and steal those electrons. So if we look here at oxygen, so remembering if we look at our periodic table, with the exclusion of the noble gases, as we move left to right and bottom to top, the electronegativity goes up. Now, seeing as oxygen is about here on my very crude diagram, oxygen is really electronegative, extremely electronegative. So it really, really wants to steal those electrons. It wants them bad. Hydrogen, on the other hand, hydrogen's over here. So hydrogen's really not that electronegative. It's not really wanting to steal all of these electrons. So what happens here is, as these electrons are being shared, okay, oxygen is going to be that greedy kid who wants to hang on to that ball a little bit longer. So it means that the electrons are going to want to hang around up here. So that's going to mean that oxygen is delta negative, whilst these hydrogens are delta positive. Okay, we can see that the electrons are going to spend more time on this side than what they will on this side. And that, in essence, is polarity. Okay, the next one is write the Lewis structures for the following. Now, I want you to pause this video, have an attempt yourself, and then we'll work through it together. So the first one is write the Lewis structure for gallium. So gallium, if we have a look on the periodic table, and again, we only look at the S and P subshells, we will see that gallium has 3 valence electrons. So if we write gallium, and that's it. That is the Lewis structure for gallium. Now the next one is where it gets a little bit tricky. So we have gallium, but it's 3+. So if we were to write gallium, what is the charge of gallium with its 3 valence electrons? And the answer is 0. It's neutral because its number of electrons are equal to its number of protons. But if we have a look up here, we see that it contains a charge of 3+. So that means that the overall charge of gallium has gotten more positive. Now, a good way of thinking about this is if you hang around, like, because electrons are negative, if you get more electrons, the charge of the element gets more negative. If you lose electrons, if you lose those negative charges, the charge of an overall element or compound gets more positive. So a good way of thinking about this is if you hang around something who's really mopey, really depressed, really, just down and out all the time. So if you hang around someone who's really negative, you will start to feel really negative. Whereas if you remove those negative or angry people from your life, you get more happy. Coming back to our little example here, so we have our gallium, but it's saying 3+. So that means it has lost 3 electrons. So if it loses this electron, and this electron, what is the Lewis structure? Well, because it lost all of the electrons in its outermost shell, it drops down an energy level. Okay? So it will look like this. Because essentially, by losing those 3 electrons, it dropped down to a lower energy level. And because it dropped down to that lower energy level, it then had all 8 of its valence shell, the valence electrons fulfilled, and it means that it is stable. So a lot of, this is a good question that really shows the common traps that students fall into, because a lot of students think, oh, okay, it lost 3 electrons, so therefore gallium must have 0. It mustn't have any valence electrons. And again, this is where I remind you about that octet rule. These are all in energy levels like this. So if gallium had 3 electrons in its outermost shell, but it had 8 in its lower energy level, and it lost these 3 electrons, then that means that this shell here doesn't exist anymore, because there's no electrons there to occupy it. And that is why gallium reverts back to this, and it has 8 electrons in its outermost shell. Okay, so let us look further into Lewis structures because they are just simply so important. So let's look at H2S. So if we look at H2S, and we look at our periodic table to see how many valence electrons it has. So if we have a look, sulfur has 6. Now this example is very much, it's basically identical to our water example that we were looking at before. So we've got our hydrogen, so we represent 1 electron there. So sulfur, 1, 2, 3, 4, 5, 6, 7, 8. So sulfur is stable. Hydrogen, 1, 2. Hydrogen, 1, 2. Everyone's happy? Happy days. That is the Lewis structure for H2S. The next one that we'll be looking at is now NH3. So NH3, we look at, so it's the same deal. We write nitrogen, and we write the valence electrons for nitrogen. So nitrogen has 5 valence electrons. Now, something very important to note here is that we have a lone pair of electrons. So remembering when we're doing Lewis structures, when we're doing our Vesper, it's very important to be aware of those lone pairs. Now, same deal, we go through and we make sure all of them have 8 electrons in their outermost shell, with the exception of hydrogen. So nitrogen is 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen, 1, 2, 1, 2, 1, 2. So that is the Lewis structure for NH3. Now the next two that we're going to attempt are much more challenging, and this will take a lot more working out in order to get our Lewis structure. But as long as we follow the same pattern as before, we'll be fine. So draw the Lewis structure for the following: CO3 minus 2. So by looking at the periodic table, carbon has 4 valence electrons. However, because of this minus 2 over here, this compound has 2 extra electrons that were taken from somewhere. We don't know where, and that's fine. That's not our concern for this particular question. So I'm going to draw in an extra 2 electrons, because that is what this minus 2 represents. So remembering, oxygen has 6 valence electrons. Now, I haven't put the valence electrons for oxygen in any particular order or special way. I just wrote them so that they all have their 6, and we're going to rearrange and move them all around now. So again, our key rule here is we need to make sure that all of these elements have 8 electrons in their outermost shell. So we have a look at oxygen, 1, 2, 3, 4, 5, 6, 7. So not happy. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Oh, hello. Now, carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Holy dooly. Okay, so we know that's wrong, but there's a problem here in that we've never really had an element that has too many electrons. We've always dealt with problems where they have not enough. So this is where we need to have our wits about us, and we need to shuffle things around so that each of them have 8. So we know carbon has got too many. So that rings a bit of an alarm bell for me. And that tells me, okay, because carbon has too many electrons, it can actually donate them. It doesn't need to share, because it's going, I just want 8. I don't want 10. So what will happen is, if we move, we rearrange this lone pair up here. So what I've done is I've just redrawn those electrons to put them in a different spot. Carbon still has the same amount as when I started before. So what I've done is I've just redrawn this Lewis structure, make it a little bit neater. But we can see here that there is no need for oxygen to share its electrons. So what carbon is doing, because remember, carbon had too many electrons before, is these pair of electrons here are working as a covalent bond, so they're being shared between the oxygen and the carbon. But the thing is that oxygen doesn't have to share any of its own electrons between carbon. So this is still a covalent bond because these electrons are being passed from carbon to oxygen, but essentially oxygen still retains all 6 of its electrons. It doesn't share them. So if we go through and we count them again, so we have 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's happy. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And carbon, 1, 2, 3, 4, 5, 6, 7, 8. Now, when we finish our Lewis structure here, I draw the whole thing in a square bracket and put -2 to indicate that this overall compound has got 2 extra electrons. And that is the Lewis structure for CO3. Now, if we look at our next one, NO3-, we follow the exact same rules and procedure in order to identify its Lewis structure. So nitrogen. Now, nitrogen again has 5 valence electrons in its outermost shell. But again, the trick is that we have this little minus symbol. So that means that there is an extra valence electron within nitrogen. Now we have our 3 oxygens over here. Now again, by quickly counting through all of these, you will see that all of them are not happy. And it's going to be the exact same problem that we had with CO3 up here. And again, by rearranging these electrons so that it forms something like this, we can see that all of these are now stable. They all have 8 electrons in their outermost shell. So we can see there's 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So again, after drawing this Lewis structure, put a square box and put a negative symbol. Again, to show that this compound has 1 extra electron. Okay, so let us now move on to question 40 on page 246. Use VSEPR theory to predict the shape of these molecules. So again, when we're looking at VSEPR, it's very important to make sure that you draw the Lewis structure out first. Because by drawing the Lewis structure, you can see the lone pairs. Now, if there are any lone pairs of electrons, they do affect the overall structure of a compound. And that is a big thing that students often forget when they're trying to do these sorts of questions. So, as we have a look at silicon tetrafluoride, we write silicon. Now, looking at the periodic table, we would see that silicon has 4 valence electrons. Now, we have a look at fluoride. Okay, so there are 4 fluorides. So now, again, we do a quick count, make sure that everything has 8 electrons in its outermost shell. So 1, 2, 3, 4, 5, 6, 7, 8. So silicon's happy. And fluorides have got 7 and 1 is 8, 7, 1 is 8, blah, blah, yes. So they're all stable, happy days. Now, the next thing we ask ourselves is, are there any lone pairs? So we have a look here. And when I say lone pairs, I mean lone pairs in regards to the central atom. So we don't need to worry about lone pairs such as these. They're not relevant in this case. So are there any lone pairs around here? The answer is no. So the next thing we need to do is we need to acknowledge, okay, how many chemical bonds are formed? So because we have silicon that is bound to 4 lots of fluorine, then we know that it must be a tetrahedral. Now, the reason why it does form this tetrahedral shape is, if I just... So this is how I draw it in 2D. Now, the angle here between these two is only 90 degrees. Now, remembering that the way these electrons repel each other is the exact same principle as having two magnets that want to push each other away. So they want to be as far spaced apart as possible. So 90 degrees doesn't cut it. What it will do is it will look more like this, where the bond angle is 109.5 degrees, and that means it's as further spaced apart as possible. So how this looks in real life is that it is essentially a tripod. So I've got one coming flat with the screen, one poking out, and one going in. Now, it's not necessary for you to be able to draw any of these, but it's important for you to visualize it, to be able to understand that molecules are not, floating 2D letters, that they are in fact three-dimensional shapes. The most important thing to be able to acknowledge and do is to see that we have silicon that is bound to 4 different substituents, and that there are no lone pairs. So that tells us that it is a tetrahedral. Now, the next one that we're going to look at is OF2. So again, we draw our central atom connecting to 2 lots of fluoride. Now we check if they're all got 8, so 7 and 1 is 8, 7 and 1 is 8, 2, 4, 6, 8. So everything is happy. Now, this is where a lot of students fall into this trap. So the shape of this is bent, because it's going to look like this. Now, a lot of students do fall into the trap. Instead, they will draw this. And they'll say, but, look at this, all of them have their all outer shell field, they're all connected, it's all good. But the thing is that they haven't looked into the outer valence electrons. They haven't looked into the lone pairs. And this is where this is so important, because what is VSEPR? What's causing these electrons to repel, to push each other away? Electrons. So if we have a pair of electrons, they're going to work exactly the same as a bond to another atom. They're going to push things away from it. So because the difference here between the pair of electrons over here and the pair of electrons which are connecting the fluorine and the oxygen are only 90 degrees apart, they're still too close. And this is why, instead, it will form this shape, because these lone pairs of electrons will push them down. Okay, next one, page 246, question 59. So I want you to pause this video and attempt the question first. So estimate the bond angles between the atoms in these molecules. So let's have a look here at carbon dioxide. So we've got our carbon that has 4 valence electrons, and we have 2 oxygens. Now I'm going to draw them here. It really doesn't matter where you draw them, because it's the same as when we were doing our more complicated Lewis structures, because we're going to move them all around anyway. So oxygen, remembering, has 6 electrons in its outermost shell. Now we check to see if they all have 8. So 2, 4, 6, 7. 2, 4, 6, 7. And 4, 5, 6. So all of them are not stable. So what's going to happen is that this electron's going to drop down, and this electron's going to come up, and this one's going to come up here. It doesn't matter which one of these you choose, just as long as they form a pair. And what's going to happen is we're going to have this. It's going to form a double bond. So remembering, a bond is just 2 electrons. So when we have a double bond, we have 2 lots of 2 electrons. Now, what is the bond angle between the atoms in this molecule? The answer for carbon dioxide is 180 degrees because it's linear. Now, I may hear you asking, well, hang on, bro. You said that we had OF2 in the previous example, but that wasn't linear. You said that was bent. And this is a perfect example of, again, make sure you take into account those lone pairs. Because as we look over here, there are no lone pairs up here. And there are no lone pairs down here. So because of the absence of those lone pairs, there's nothing there to sort of push the atoms up or down. So because of that, they simply go one on either side, which means that they are 180 degrees apart. And it's pretty tough to get any further apart than that. So the bond angle between carbon dioxide is 180 degrees. Now, the next one that we're going to look at is NH4+. Now, again, we've got to pay very close attention to that plus charge. So we have nitrogen. 1, 2, 3, 4. Now, I only draw 4 valence electrons because this is positive. So if it's positive, it means it has lost an electron. And because it lost that electron, it means that it only has 4 instead of 5. So it has 4 hydrogens, so we draw those in. And again, we count them to make sure they're all stable. So nitrogen, 2, 4, 6, 8. So nitrogen is happy. Hydrogen, 2, yes, 2, 2, and 2. So everything is all nice and stable. Now the next thing that we do is we look at our lone pairs. So we go, okay, in here, are there any lone pair of electrons? So we look here and we go, no, there isn't. Then we ask ourselves, okay, how many atoms or substituents are bound to this nitrogen? So we can see that we have 4 hydrogens. Therefore, the answer is tetrahedral. Tetra meaning 4. So because this is tetrahedral, you should have memorized that the bond angles between tetrahedral molecules are 109.5 degrees. And again, that must be memorized. Okay guys, that now wraps up our Module 5 Video 2 tutorial video. I hope you all enjoyed it. Thank you all very much for watching. If you have any questions or queries or anything like that, feel free to email me at b.grant@griffith.edu.au. There is a survey just underneath this video in the description panel. If you guys could all just answer that, it's a very short 3-4 questions. That would be great, as it gives me a lot of feedback on these videos and how to constantly improve them and make them better. I hope you all enjoyed this video. Keep up the hard work, and I'll see you all next time.